Hello class, welcome to this video on the Chapter 7 test review. So we're going to look at the other version of the test. So let's look at the multiple choice first. According to the US Census Bureau, 23.5% of people in the United States are under the age of 18. In a random sample of 250 residents of a small town in Ohio, 28% of the sample was under 18. Which one of the following statements is true? Okay, so here it says according to this, it's a census. So a census is when you take the entire population, right? So in this case, if you look at the first part, 23.5% and 28% are statistics. 215 and 18 are parameters. No, 250 is a sample. This is a sample of 250 residents, and then 28% of the sample was under 18. So that 28% is a statistic because it comes from a sample, but 250 is also something that comes from the sample. Okay, so it's not a parameter. All right, 23.5% and 28% are parameters. 28% is not a parameter. 28% is a statistic. Remember that statistics come from samples. So you got a sample. You got a statistic from a sample. If you got a population, parameters come from the population, okay? So 23.5%. So the best answer here is E. 23.5% is a parameter because that comes from the entire population. And then from the sample, 28% is a statistic, okay? So that's what we're looking for. All right, so remember that statistics are measures taken from a sample, parameters are measures taken from a population, and so these are measures taken from the population and sample respectively. The best statistic for estimating a parameter has which of the following characteristics? So it's just a matter of understanding the idea of the unbiased estimator. So again, unbiased meaning no bias, so ideally you want low bias and low variability. Okay, the answer is D. All right, olive weights are classified according to a unique set of adjectives implying great size. For example, the mean weight of olives classified as colossal is 7.7 grams. Suppose a particular company's crop of colossal olives is approximately normally distributed. There it is, normally distributed, with a mean of 7.7 and a standard deviation of 0.2. Which of the following represents the probability that the mean weight, guys, that means X bar, right, of a random sample of 3 olives, that's N, and this is mu, and then this is sigma, from this population is greater than 8 grams. Okay, so we want the probability that X bar is greater than 8. Okay, so remember that this is approximately normal, and because we have a big enough sample size, and so remember that the mu X bar is equal to the mu, which is 7.7. The sigma X bar, this is the sigma for the X bar distribution. This is the central limit theorem, okay, is sigma over square root of N. All right, so we need to calculate those first. So we got sigma over square root of N, that's 0.2 is the standard deviation divided by the square root of 3 olives. All right, so let's do that here. We got 0.115. All right, and then we're going to remember that we're doing greater than 8. So that means when we do it, we're going to use normal CDF. And the lower limit is 8, and then the upper limit is infinity, or we're going to a really big number. So you got lower is 8, upper is big number, so 10 to the 9th. And then our mean is 7.7, and our standard deviation is 0.115. Okay, we're going to do that and get, if you were to do that, your answer would be A. Okay, and then you can also calculate this using z-scores, so we'll show you how to do that as well, just so you are familiar with the calculation. Okay, so z is equal to x bar minus mu x bar divided by sigma x bar. That's how you calculate the z in general. But remember that mu x bar is just equal to mu, right? And then sigma x bar equals sigma over square root of n. And so you just have to plug in the numbers. The x bar was 8, right? Minus the mu was 7.7 divided by, and we already calculated this, so let me just put that number there. And you would get a z-score, you would get a certain z-score, and then you would look that z-score up in the table to get your answer. So let's see what that z-score is. So you get 0.3 divided by 0.115, so 2.61. Okay, and we look up 2.61 in our table. Yeah, so we got the tables for AP Stats. So 2.61. Okay, so we got 2.61. So notice that that's 0.9955. Okay, so let's look that up. Okay, so we got 0.9995. And remember, the table gives us the area to the left. So when we do 1 minus that, we get 0.0005, which is really close. Oh, sorry, 0.9955, not 0.9995. There's 2 5s there. So 0.0045. Okay, so which is round, so that's pretty close to what they got there, 0.0047. All right, so the answer is A. Well, also, if you want the formulas for the sigma x bar and all that stuff, just look over right here. So you got for sampling distributions, sorry, let's see if I can find it. Should be, oh, right here. So mu x bar is mu, and then sigma x bar equals sigma over square root of n, okay? All right, so let's take a look at the next problem. All right, so next one, number 4, population 1 is normally distributed with a mean of 40 and a standard deviation of 4. And population 2 is normally distributed with a mean of 25 and a standard deviation of 7. Suppose we select independent SRSs of n equals 100 and n equals 85 from population 1 and 2 respectively. Which of the following are the values of the mean and standard deviation? So we just want to calculate the mean and standard deviation for there. All right, so let's check on our formula sheet. So we have a difference of 2 means, x bar 1 minus x bar 2. So we're looking for, there it is, 2 populations, x bar 1 minus x bar 2, and this is your mean and your standard deviation right there. So we're going to use those 2 formulas, all right? Okay. So here we go. We got mu x bar 1 minus x bar 2. That's just mu 1 minus mu 2. All right, population 1 has a mean of 40. And it has a mean, population 2 has a mean of 25. So you just got to subtract those. 40 minus 25 is 15. So that eliminates D and E. All right, so now let's do sigma x bar 1 minus x bar 2 is equal to square root of sigma squared 1 over n1 plus sigma squared 2 over n2. So we got sigma. So now this is sigma 1. Is 4. For population 2, the standard deviation is sigma 2 is 7. So we got 6 squared, and then n1, they said is 100, and n2 is 85. Okay, so we got 6 squared over 100 plus 7 squared over 85. All right, so it's got to be A. Or wait, no, that's it. They use 4 there. Is there a typo there? Let me see. Oh, I used the wrong number here. So sigma is 4 right here. So it's 4 squared. All right, so we got A is our answer. All right, so number 5, an electronic prize wheel is programmed to land on win 25% of the time on weekdays and 10% of the time on weekends. And consecutive plays produce winners independently. Suppose we observe a random sample of 50 outcomes from this machine on weekdays and 100 outcomes from this machine on weekends. Let P hat WD and then P hat WE be the sample proportions for weekdays and weekends respectively. Which of the following describes the shape, mean, and standard deviation of the difference of the two proportions? Okay, so in order to test whether they're approximately normal, remember it has to satisfy the large counts condition. So let's see if that's the case here, and it's got to satisfy it for both weekends and weekdays. All right, so we need the n for weekdays times the p for weekdays. We need the n for weekdays times 1 minus p for weekdays. We need the n for weekends times the p for weekends. And we need the n for weekends times 1 minus p for weekends. We need all of those to be greater than or equal to 10. All right, so it says it's programmed to land win 25% of the time. So that's P WD for weekdays. This is P WE for weekends. And we got 50 outcomes on weekdays. So that's N WD, 100 for weekends. Okay, so we got 50 for the number for the weekend or weekdays times 0.25%, 25% of the time. And this is 1 minus. And then for weekends, it was 100 outcomes times 10% success. 100 times 0.10 is 10, so that's greater than or equal to 10. This is a fourth of 50 is definitely greater than or equal to 10. And 75% of 50 is definitely greater than or equal to 10. 90% of 100 is definitely greater than or equal to 10. So this one was the only one that was kind of borderline, but it made it. It made the cut. And so therefore it's approximately normal. All right, so that eliminates D and E. So it's got to be A, B, or C. And then we can calculate the mean. So let's calculate the mean. So the mean P hat 1 minus P hat 2 is just the difference in the two means, okay? And we get that from the formula sheet. And we also get from the formula sheet sigma P hat 1 minus P hat 2 is the square root of P1 times 1 minus P1 divided by N1 plus P2 times 1 minus P2 divided by N2. Okay, let me show you where that is on the formula sheet. So you go for proportions, and then you get right here, P1 minus P2, and then we get this one right here, okay? All right, so there it is on the formula sheet. So let's go ahead and apply it here. All right, so we got P1 minus P2. P1 is WD, okay? So we're gonna say weekdays minus weekends, because that's what they said, okay? So weekday and weekend. I'm just gonna do that so that I can remember. All right, so we got weekday was 25%, weekends was 10%. So you subtract those and you get 0.15. All right, and then calculate this, square root of 0.25 for weekdays, 1 minus 0.25 over 50 outcomes for weekdays. And then we got probability, the success for weekends is 10% times 1 minus 10%. Or 1 minus 0.10, and then divided by 100. Okay, and you can do that, and you get get the calculation, and your answer is going to be A. Right here, the standard deviation is 0.07. There's your mean. Okay. All right, number 6. A local news story claims that 53% of high school males agree with the statement, "I am okay with a girl playing on the football team because there's not a football team for girls." All right, so to investigate this claim, an SRS of 100 males from a large local high school is selected. In the sample, 38 males agreed with the statement. We use technology to simulate 240 simple random samples of size n equals 100. All right, and then it says the dot plot. So we got the dot plot for the sample proportion. Is there convincing evidence that less than 53% of all males at the school agree with this statement? Okay, so let's see from the graph here. Okay, and so what we got to do is for this graph, we got, it says 38 males agreed with the statement from the sample out of 100, right? So we got 38 males out of 100. So that's our p hat, which is 0.38. That's what we got from our sample, right? And we're using this dot plot to help us with that. So what is the probability that we would get a value of 0.38 or smaller? Well, 0.38 is around here, right? And notice that there are no people in our sample. There's no people in the simulation. So the probability that we would, from our simulation, the probability that we would get something as low as 38%, assuming that the original statement is true, that it was 53%, is nothing, right? So we don't get any. So that means it's too small. The probability is too small. It's unlikely to happen, and therefore we have evidence against on the contrary. We have evidence to dispute the claim that it was not 53%. Okay, so it would be very surprising to get a sample proportion of 0.38 or less in a simple random sample of size 100 when p is 0.3. Yeah, that's true. All right, remember the cutoff for that is about 5% usually. Okay, it's less than or equal to 5%. All right, so which of the following distributions has a mean that varies? Okay, so the population distribution, that's just for the population, that has a fixed mu. So mu is fixed there, right? The distribution of sample data, well, the distribution of sample data, the sampling distribution of the sample mean is also fixed, right? So the mu x bar is fixed because remember that mu is equal to mu x bar, right? That's not going to change. Whatever the population is, that's fixed, and therefore the sampling distribution is fixed. The only one that varies is the distribution of sample data, because remember, every sample yields a different result. And so therefore, when you take a sample, you're going to get a different mean every single time. So if I take a sample of 5 people and then I calculate the x bar, that's going to be different than if I take another sample of 5 people and take another x bar. So this is going to be my sampling distribution here. This is going to be my sampling distribution here, but the mean varies, right? Or not my sampling distribution, my distribution of sample data. And so the only one that varies is 2. So the answer is B. All right, so number 8, there are 120 students at Francis Howell North High School. Mr. Willott conducts a poll that asks 20 randomly selected students how many hours of sleep they got last night. They find that the mean amount of sleep is 6.7 hours. Okay, so there's 220 students at the school. They asked 20 randomly selected students. There's your mean. There's your standard deviation. Can we estimate the standard deviation of the sampling distribution of means by using this calculation? Can we do that? Well, and the answer is that, well, you can use this formula as long as the 10% condition is satisfied. Okay, so if the 10% condition is satisfied, then that formula yields an accurate result. It'll be a good estimate of what the standard deviation is. If you do not satisfy the 10% condition, it's going to be a different value, significantly different. So in this case, we have 120 students in the population. That's what they said. There's 120 students at the high school, but you select 20 of them. Well, 20 out of 120, if you calculate that, right? 20 out of 120, that's 16% of the population. 16.7% of the population, right? Which is not less than or equal, which is not less than 10%. It has to be less than 10% of the population, okay? And therefore, we cannot, right? So the answer, no, because the sample is more than 10% of the population. So the answer is D, okay? All right, number 9. You take a simple random sample of size 25 from a very large population in which the true proportion is p equals 0.1. Which statement below best describes what you know about the sampling distribution of p hat? Okay. All right, so the simple random sample is a size 25 from a very large population. That means 10% satisfied, 10% condition, which means that you can use the sigma p hat formula, right? So that's fine. So let's check on that. 10% condition means you can use that sigma formula. The true proportion is p is equal to 0.1. So we know that this is going to be 0.1 regardless, because a p hat is an unbiased estimator. So then, it says you have a sample size of 25 with a proportion of 0.1. So if we do NP, that's 25 times 0.1. That's equal to 2.5, which is not greater than or equal to 10. Not greater than or equal to 10. And so that means it's not normal. Okay. So if it's not normal, it can't be C or E. And it says we cannot use the formula. No, this is not true. We can use the formula, right? Because we satisfy the 10% condition. And then it says, so that means it has to be A or B. Now, is the distribution going to be skewed right or skewed left? Well, because we established that it's not normal, and then you look at the p value. When you look at the p is 0.1, which means that most of the data are going to be on the small scale, right? This is 0.5 here. Most of the data is going to be on the left side because they have a higher proportion of success there. And so it's going to look like this, where most of the data is at 0.1 and a very few is beyond that. And so it's going to be skewed right. Okay, so the answer is A. All right, so number 10, the number of siblings an individual has varies from student to student. The distribution of number of siblings is strongly skewed to the right. The central limit theorem says that. Okay. The central limit theorem. As we look at more and more students, their mean number of siblings gets ever closer to the mean mu for all students. No, that's not what the central limit theorem says. The mean number of siblings for any number of students has a distribution of the same shape strongly skewed as the distribution for individual students. No, that's not what it says. The mean number of siblings for any number of students has a distribution that is close to normal. For any number of students, no. It has to be, remember, the idea of the central limit theorem is that as you get greater than or equal to 30, large sample, as your sample size is large enough, then it's going to approach a normal distribution. The mean of the sampling distribution of sample means. Okay, the mean number of siblings for a large number of students has a distribution of the same shape as the distribution for individual students. No, so it's not A, B, C, or D. It has to be E. The mean number of siblings for a large number of students has a distribution that is close to normal. Yes, the mean number of siblings. That means the X bar distribution is going to be close to normal for a large number. All right, it's E. All right, so let's look at a few of the fear response. All right, so part 2. The distribution of actual weights of 8-ounce chocolate bars produced by a certain machine is normal with a mean of 8.1 ounces and standard deviation 0.1 ounces. Company managers do not want the weight of a chocolate bar to fall below 8 ounces for fear that consumers will complain. Find the probability that the weight of a randomly selected candy bar is less than 8 ounces. Okay, so randomly selected candy bar, so that means they're talking about X. So they want the X to be less than 8. So if we were to draw the graph, then if this is 8, then it's going to be less than. So when we use normal CDF, right, we're going to use normal CDF here. Actually, let's do it all out. Do the graph and then the Z and then normal CDF. Okay, so let's just do it all out. All right, so we want the probability that X is less than 8, and we got ourselves a normal distribution. So let's do a normal distribution. And now the mean is 8.1, and standard deviation is 0.1. So we're going to start at 8.1 in the middle, and then we're going to go by 0.1s. So 8.2. 8.3, 8.4, 8.0, 7.9, 7.8. And we want it to be less than 8. And this is 8 right here. So we want to shade the area to the left there. Okay, and so now we're going to convert this to a z-score. Okay, so let's convert this to a z-score. So z is x minus mu divided by standard deviation, and the x is 8, right? So we got 8 minus the mu of 8.1 divided by the standard deviation of 0.1, and so this gives you a z-score of negative 1.0. And then, so that's what we get here, negative 1.0. And so we're going to look that up and on the table to see what we get. Okay, so let's look that up real quick. All right. We got negative 1.0. So this is, these are pretty big negative numbers. So let's go over here. There it is. So negative 1.00. So the the area is 0.1587. Okay, 0.1587. Let's go back to our question here. All right, so the area is 0.1587. And that's the probability that a randomly selected candy bar is less than 8 ounces. So we got that probability. And that's how you do it with the z-scores. Remember that the table gives you the area to the left, and therefore we got our answer. If the table, if you want the area to the right, simply subtract from 1. All right, so let's also show you this with the normal CDF. So normal CDF, the lower is negative infinity, so a really big negative number, and then the upper is 8, right? And then the mean is 8.1. The standard deviation is 0.1. And you should get a similar result to this. All right, so 40 candy bars is selected at random and their mean weight X bar is computed. All right, so now we got 40 candy bars are selected, so that's n equals 40. Calculate the mean and standard deviation of the sampling distribution of X bar for samples of size 40. All right, so this is just the formula. So mu X bar is just equal to mu. That's from the formula sheet. And the mu is just 8.1, right? So we already know what that is. Done. And then the standard deviations, sigma X bar is equal to sigma over square root of n. Now remember, we can use this formula as long as it satisfies the 10% condition. So in this case, we got a sample of size 40. We're assuming that that's, it says is the certain actual weights of 8-ounce chocolate bars produced by a certain machine. We're assuming, so I'm going to put a little condition here. So assume n equals 40 is less than 10% of all candy bars. Okay. So we're assuming that, and then we can calculate this. All right, so sigma is, we said it was 0.1, so 0.1 divided by square root of 40. All right, let's see what that is. 0.1 divided by square root. All right, so you get 0.0158. Okay. And it's going to be in ounces, of course. Oops. Not sure why that's still there. All right, so we got a little glitch in the video there in the computer, so I lost my information there for some reason. But let's go ahead and continue. So, so as we said, the standard deviation that we got was 0.0158, and then the mean for part B, which I don't have here anymore, is the same mean as we had in part A, which again I don't have, but it says that the mean was 8.1, so that's going to be the same mean in part B, and then the standard deviation is 0.1 divided by the square root of 40 candy bars, which is 0.0158. So let me just at least write those down. All right, so now part C, find the probability that the mean weight of the mean weight, so that's X bar, of the 40 candy bars is less than 8 ounces. Okay, so the mean weight, the probability that the mean weight is less than 8 ounces. So when we are calculating this, remember that we're doing X bar is less than 8. So it's going to be, when we do the normal CDF, we're going to keep this picture in mind. But let's calculate the z-score. So the z-score is X bar minus mu X bar divided by sigma X bar. All right, we're dealing with X bars. That's why I make sure to include the mu X bar and the sigma X bar. But we know mu X bar is just mu, okay? And we know X bar is 8. So 8 minus 8.1. The numerator stays the same. The denominator, however, changes because it's 0.0158 this time, okay? And so we calculate the z-score. Let's see what that is. So it's going to be negative, of course. So 0.1 divided by 0.0158. So negative 6.33 around there. Okay, that looks like that's what we get. So now, if you see a z-score that is that small, negative 6.33, that far on the left side, well, let's look in our table. Okay, so let's see what this looks like on our table. So we go on our table. Notice that the smallest z-score that you have, the most negative that you have, is negative 3.49. But look how small that value is, 0.002. That means if you're past that point of negative 3.5, you're practically 0, okay? 0.000000, especially if you're negative 1.6 something, all right? So this means that this is equal to the probability that z is less than negative 6.33, which is practically nothing. So it's approximately 0. And again, if you did this with normal CDF, you would get a very a very small number, similar result. Normal CDF, negative, we got to show our work here. This is the only bad thing about having to use calculator speak, is we got to write it all out there. Lower is negative 10 to the 9th. Upper is 8. Mean is 8.1. Standard deviation is 0.0158. Okay, that's your normal CDF function, and then calculate that. Now, would your answers to A, B, or C be affected if the weight of chocolate bars produced by this machine were distinctly non-normal? Explain. Okay, so let's look at part A again, since we lost it, but we could still look to see. This was the probability that the weight of a randomly selected candy bar is less than 8 ounces. So we would not, the only reason we were able to do this calculation is we knew that it was a normal distribution. Okay, if we do not know that if it's non-normal, then we will not be able to do this calculation. However, for part B and C, the calculation will not be affected, because notice that the size 40, that's greater than or equal to 30 anyways. And so we know that the distribution is going to be normal as long as that condition is satisfied. And so we can proceed with the normal distribution calculations, okay? So we would be unable to do calculation in part A. However, we could do parts B and C. Okay. We could do parts B and C because n is greater than or equal to 30. and therefore the CLT guarantees normality, or approximate normality. Okay, so that takes care of number 11. Okay, number 12. Mrs. Bracken asks a random sample of 500 adults whether they favor giving vouchers to parents of school-age children that can be exchanged for education at any public or private school. Each school will be paid by the government on the basis of how many vouchers it collected. Suppose 45% of the population favors this idea. What is the mean of this sampling distribution of p hat, the proportion of adults in sample size, n equals 500, who favor giving parents of school-age children these vouchers? All right, so we know it says suppose 45%. So that's the population. Suppose that that's the population, right? And what is the mean of the sampling distribution of p hat? All right, so the formula for that, the mean of sampling distribution of p hat, that's just going to be p. So if you go to your formula sheet, that's going to give you the mu of p hat is just p. And they said that p is 0.45, okay? All right, and then they said the n is 500, so we might need that for later. We'll need that for the standard deviation for sure. All right, so remember, to calculate the standard deviation of p hat, first off, we need to satisfy the 10% condition. Is that work here? Well, we got a sample of 500 people, and these are adults, whether they favor giving vouchers to parents of school-age children for any public or private school. We can assume that if we're talking about all adults, that's going to be, that 500 is going to be less than 10% of all adults, right? That, and whether they favor giving vouchers to parents of children, right? So they're talking about all adults, okay? All right, so we can assume 10% condition is satisfied here, and so we can say sigma p hat is square root from the formula sheet, p times 1 minus p divided by n, okay? And so we get square root, and the p is 0.45 times 1 minus 0.45 divided by n is 500. All right, and you calculate that, and you get about 0.0222. And we want to interpret this value, so that's what they said, interpret. Okay, so we would say to interpret this value, the proportion of adults who favor the vouchers for parents of school-aged children typically varies from the mean of, from the mean of 0.45 by approximately 0.0222. Okay, so there you go. So that's the interpretation. So check that you can use the normal approximation for the distribution of p hat. Okay, so we got to do n times p, which is 500 people times 0.45. And we calculate that, we get 225, which is certainly greater than or equal to 10. And then we do n times 1 minus p, so we got 500 times 1 minus 0.45, which is 275, which is greater than or equal to 10. So that's true. All right, so therefore, yes, it is approximately normal. All right, so D, what is the probability that more than half of the sample are in favor? More than half, okay, so that means the probability that the p hat is greater than 0.50, right? Okay, so we can easy to just use the normal CDF. We can of course calculate the z-scores, which I can show you how to do that as well. Okay, so z is equal to p hat minus mu p hat divided by sigma p hat. And the p hat is 0.50. The mu p hat, that's the average. We calculated this earlier. The mu p hat was 0.45. And then the sigma p hat was 0.022. So we get 0.05 divided by 0.0222. So 2.25 for my z-score. All right, so remember that if the z-score is 2.25, you're over here, and we want it to be greater than 0.50, right? So that means that when we look it up from the table, we need to subtract from 1, okay? But let me look at the value from the table, see what we get. So we get, that's for negatives. Looks like for positives here. All right, so we got, so we got 2.25. So we get 0.9878. That's the area to the left, so we got to subtract from 1, right? All right, so then the probability is 1 minus 0.9878, which is 0.0122. All right, and then if we use the normal CDF calculation, we get our lower is 0.50. Our upper is infinity, so we're just going to do a really big number. Our mean is 0.45, and our standard deviation is 0.0222. And we get a similar result. Okay, all right, so then part E, if a second sample of 500 is selected, what is the probability that those two sample proportions are less than 3 percentage points apart? Okay, so that means that they're saying, okay, now we have a second sample, so that means we're the p hat 1 minus p hat 2, that they're less than 3 percentage points, so less than 0.03. That's what they're saying. Okay, if I subtract them, so that's the so that's what we want. So we want the probability that that is less than 0.03. All right, so remember we got to calculate the mu p hat 1 minus p hat 2. That's 0. That's going to be the same thing as mu p hat 1 minus p hat, or p1 minus p2. Okay, you can look this up in the formula sheet. P1 and P1 and P2 are the same, right? So they're both 0.45 because they come from the same, population. So they're both 0. It's not like they're two different populations. They come from the same population. So we know when we subtract them, it should be 0. And then the sigma p hat 1 minus p hat 2, well, the formula for that is P1, P1 times 1 minus P1 divided by N1 plus P2 times 1 minus P2 divided by N2. All right, but remember that N1 and N2, these are all the same thing. So 0.45, 1 minus 0.45 divided by 100, or 500, sorry. And then we just add it to itself, right? So it's just repeating again. All right, so when we do this, we get 0.0315 for the variability, the standard deviation. And so now we can calculate the probability, and this time we're just going to use normal CDF, okay? Just to be complete, I will show you the formula for the z-score, okay, just so you have it. All right, so p hat 1 minus p hat 2. Let me see if I can... Oops, sorry about that. P hat 1 minus p hat 2. All right, so p hat 1 minus p hat 2 minus mu p hat 1 minus p hat 2 divided by sigma p hat 1 minus p hat 2. Okay, so that's basically your z. It's the parameter minus the mu divided by standard deviation, and then the p hat 1 minus p hat 2, that's just 0.03. And then the mu p hat 1 minus p hat 2, that's just 0, right? And then the sigma p hat 1 minus p hat 2 we found was 0.0315. So when you calculate the z-score, you get 0.03 divided by 0.0315, so 0.95 should be your z-score. And then you can look up on the table and all that stuff. But I'm going to use the normal CDF function here, okay? So normal CDF are lower. Remember, it's got to be less than 0.03. So if this is 0.03, it's got to be less than that. So the lower is negative infinity. So lower is negative 10 to the 9th power. Upper is 0.03. Mean is 0. Standard deviation 0.0315. And when you do this, you get approximately, you get about 0.65. Let's see. Oh wait, something's wrong with it with this because I think it says, let me go back. It says are less than 3 percentage points apart. Okay, apart. So let me make a correction here. If it's less than 3 percentage points apart, then that means this has to be between 0.03 and negative 0.03. Okay, so that's what it should be saying. Sorry about that. The z calculation is going to be the same and all that, of course. And the mu and sigma, it's not going to affect any calculation except for the calculator part, okay? So, and it's going to affect my graph here, obviously. So it says apart, so less than 3 percentage points apart. So that means it's going to be negative 0.03 and 0.03. So that's how it's going to affect my graph. And it's going to affect my lower and upper, obviously, right? Because that's not the shaded area. The shaded area is within 3 percentage points. Okay. All right. So it's got to be less than 3 percentage points apart. So that's it. So my lower is now no longer going to be infinity. It's going to be negative 0.03. Okay. So sorry about that. I was just going to change that part. And then so then when you get that, it's going to be. Let's see, with technology, yeah, 0.6591, 6.6591, so 65%. That makes sense from the graph, 65.9%. Okay, so now while we're at it, we might as well do the z part because now it's because of this situation. So we're going to calculate two z-scores. This z-score right here gives us the 0.95 that I wrote here. And this z-score is going to give us negative 0.95. Okay, so you would look up both z-scores and then you would subtract them and that would give you the answer. So you would look both of these z-scores up on the table and then subtract them. All right, number 13, 5 gentlemen went to Molesky's restaurant for all-you-can-eat wings. Mr. Andresen ate 6 wings, Mr. Betts ate 24 wings, and Mr. Henriksen ate 18 wings, Mr. Osters ate 20 wings, Mr. Tyson ate 32 wings. Okay, so we got 6, 24, 18, 20, and 32, and 5 is my population. We got all 5 people for that. List all 10 possible simple random samples of size n equals 2. Calculate the mean number of wings eaten for each sample and display the sampling distribution of the sample mean on a dot plot. Okay, so we have 10 possible simple random samples. So let's go ahead and list those out. So we'll just list them out here. So number 1, we could say, let's actually do A for Andresen, B for Betts, H, O, and T. Okay. All right. So we can do A and B. which means that our x bar is going to be 6 plus 24 divided by 2, which is 15. And then we can do AH, which would be x bar 2 is equal to 6 for Andreessen, and then Henriksen 18 wings divided by 2, and you get 12. We can do AO, calculate the x bar, 6 plus Oster's 820, so that's going to be 13. And we continue doing that for all 10. All right, so I went ahead and listed out the rest of them. So we got 1 through 10. There's no more possibilities. There's only those possibilities, because if I do TA, that's the same thing as AT. So there's no more possibilities here. And I went and calculated the averages of the number of wings per pair of people. And so these are my x bars. These are my sample means. This is my sampling distribution of sample means, guys. That's what this is. Sampling distribution of sample means. So if I were to graph these, that's what I would get. So let's graph the sampling distribution of the sample mean. So x bar equals sample mean number of wings eaten. All right, we want to make sure we label stuff. And we got 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26. And we're going to just plot those dots. We got one dot here. We got a dot at 13. We got a dot at 15. Got 2 dots at 19. Dot at 21. 22. 25, 26. And there's another one I forgot. There's there 28? Yeah, there's 25, 26. And of course, I forgot the 28. So I'll just extend and put the dot there. So that's my sampling distribution of sample means. Notice that it wants to, look at that. It wants to approach that. Look how symmetric that is. And that's only for a sample size of 2, right? So we know that if you do this for, large sample size, it's going to approach that normal distribution. All right, so now let's again answer the next question. Is the sample mean an unbiased estimator of the population mean? Justify your answer. So let's calculate. Let's do that. The answer is yes, but let's calculate this. So mu x bar. So we're going to do the average of these x bars. So we're going to add these up and then divide by 10 of them, right? So we get 15 plus 12 plus 13 plus dot, 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 all the way to 26. Divide that by 10. We get 20. Now, this is equal to the population mean of 20, right? How do we know what does the population mean? Well, let's do that. Let's calculate the population mean. So the population mean are these guys. So 6 plus 24 plus 18 plus 20 plus 32 divided by 5, because we had those 5 people, right? So one guy ate 6 wings, the other guy ate 24, the other one 18, the other one 20, the other one 32. And divide that by 5 people. Well, that's going to be 20. All right, so mu x bar is equal to mu. So x bar is an unbiased estimator. All right, if we increase the sample size, does the variability of the sampling distribution change? And the answer is yes, right? Increasing sample size reduces variability. because remember the formula is sigma divided by square root of n. So as n increases, then the sigma x bar is going to decrease in variability. Okay. All right, that's going to do it for the video, guys. I hope you found this useful and informative. And as usual, I'll see you in the next one.